Okay, this is the second video I've made on fields. In this video we're going to expand our understanding of fields and start applying it to some specific examples and introduce the concept of gravitational fields. So from last video we had our definition. A force field is a region in which a body experiences a non-contact force, for example gravity, or we could also consider electrostatics initially. Okay. So it's just any space where this non-contact forces are acting. So we're going to have a look at some examples of that and consider a few ideas around it. So force fields are present in the interactions between masses and static or moving charges is where we're starting from. So this interaction, this simulation here just gives us a bit of an idea about how it might work for charges. So for example here we've got a positive charge, these arrows around it showing the direction in which a positive charge would feel a force. So here a repulsion between two positive charges would act in this direction. If we move our sensor around, depending on where we put it in the field, you get your force acting away from that positive charge, and the further away you go, the smaller that force is going to get. If we introduce a negative charge, you can see here the positive charge would be attracted towards that negative charge, which is kind of what's shown by our simulation here. You can see there as we go around that negative charge we're always drawn towards it, and the positive charge we're always repelled from. Okay, these two fields are interacting, giving us quite a complex picture, and our sensor is showing us the size and direction of that force. So we need to have a little look. We're going to just focus on gravity now and look at gravitational attraction between two objects. Another simulation here shows two masses. Here we've got a mass of 50 kilograms and a mass of 200 kilograms. Up here we've got some arrows indicating the size of those forces. So you can see that as we vary the position, the distance between those two masses decreases, the size of those forces increases. It doesn't matter which one we move, you get a similar effect. And you could say the same with masses. As you vary the mass, if you increase the mass of this object, you can see the force is increased. If you increase the mass of this object, also has a similar effect. You can see the direction here is obviously an attraction between these two objects. They're getting pulled towards each other. And yeah, that's a good indication of Newton's third law. Object A exerting an attraction on object B, but that also must have an equal and opposite attraction. Object B is having an equal and opposite attraction on object A, so the two forces acting on each other. Now that's something that everybody's come across before. What that implies, if you, 300 kilograms is probably a bit much for a person. Let's go somewhere a bit more human. Okay, small mass over here is a human standing on the surface of the Earth. You can see that there is an attraction. You're feeling an attraction towards the centre of the Earth. Everybody's familiar with that. The bit that maybe you're less familiar with is there must be an equal and opposite attraction from the Earth towards you. You are pulling on the Earth too. Now the effect of that force is minimal because the mass of the Earth is so much bigger than the mass of your own body. Okay, so you don't see the effect of this, but it is there. Now then, moving back to this, force fields represented as vectors. We've already been doing this. We've got the idea that forces have size and direction. You've seen in these previous examples that the forces can be drawn using an arrow, the length of the arrow to indicate the size of the force. Force fields just basically mean you can make prettier pictures. Here we've got an example of the field around a solenoid or a coil of wire. So it's looping around here, showing the magnetic field looping around that coil. Yeah, it's just a very quick example to demonstrate what you can do with that. Similarly though, we can represent a gravitational field with gravitational field lines as well. Now, typically, in day-to-day situations, you would expect fields to act towards the ground. So, normally, this is a good enough description. This is what we've used up to now, the idea that gravity is a uniform field. However, if you zoom far enough away on a planetary scale, you've actually got a radial field around the Earth, so it can't be parallel lines. They must head out a circular path like this. In the next video we're going to look at how that can be represented in a formula and develop this idea to give us a way of working with gravitational fields around planets, satellites, suns and stars. So we'll see you in the next video to introduce some formulas.